Okay, sounds good. So actually what Barbara was talking about is a nice segue into my presentation. We developed a technology that could potentially help mass spectrometry instruments and also water mining systems. In the realm of in situ resource utilization, there are two definite steps. First one is prospecting. You have to go to the moon, figure out how much water there is, how you extract it, whether essentially there is a business case. Once you solve this very, very important problem, and that's what the resource prospector of IPA is trying to solve, at that point you can send another system that will actually extract water and other volatiles from the surface of the moon. There are two considerations that we should never forget. First one is it's not just water. There's a bunch of other volatiles, and that's really important. For some people, these other things like CO2 or hydrogen sulfide or SO2 is a good thing. For other ones who just want water, it's actually a bad thing. Because during extraction of water, hydrogen sulfide or SO2 will react with water to form a sulfuric acid. So now you have to figure out how to design your system to not just deal with water, but it's corrosive water. So that's critical. Second one is we're not going just to where there is a water. There are a few other locations, a few other parameters that we have to consider. For example, insulation. For example, slopes. Not only rovers will have a tough time going down a steep slope, but also landers. You cannot land on every single location. You have to pick locations that's relatively flat. So that's another very important consideration. So these are the two things that we should never forget. Now, concerning, there are two concerns that I always try to flag out. First one is concern of excavation of icy soil. This is work just recently completed by Jared Atkinson at Colorado School of Mines. Jared is joining Honeybee next week as a full-time employee. He's done just superb work looking at the strength of icy lunar regolith as a function of water content at cryogenic temperatures. And essentially, you have three main regimes. If you have water content above 3%, this stuff is extremely strong. If you have below 3, around 1%, it's relatively weak, and below 1%, around 0.5%, there is no real difference between that and the granular material. And that's important for excavation standpoint. If you zoom in to the material that's above 3%, this is what you get. On a y-axis, you have strength in MPa. On the x-axis, you have density, and then you have a couple of data points for different water content and also temperature. Bottom line is anything that's in PSR is going to be very strong unless water is a separate phase from regolith. So if water is like sugar and regolith is like coffee beans and they're not sintered together, it's not a problem. But if they are sintered together, it's going to be extremely strong. Couple of MPAs, this is essentially the strength of bricks and pavement. You can go all the way to like 45 MPa. That's strength of, for example, Indiana limestone. Indiana limestone was used to build Empire State Building. So that's extremely strong. Another consideration or concern is a volatile capture. This is sort of theoretical curve. On the y-axis, you have sublimation rate as a microgram per centimeter square per hour. On the x-axis, you have temperature. And it's a log scale. So as the temperature goes up, sublimation curve essentially exponentially increases. If you convert this graph into something that you can sort of understand as an engineer, you get this one. This is the time, temperature, and mass of the 1 micron particle as a function of different parameters. So on the y-axis, you have initial mass of the 1 micron particle. So mass after time t divided by initial mass. On the x-axis, you have time, and all of these curves, they correspond to different temperatures. So if you're at 70 Kelvin, you don't have to worry about it. Nothing is going to happen. But if the temperature of these ice particles get higher and higher, the sublimation rate obviously increases. At 170 Kelvin, so it's at minus 100 centigrade, you essentially have less than 2 minutes, and these ice particles will essentially sublime away. So it's a concern. Obviously, if you come with a hot rover or rover that radiates down into the regolith, you're going to be losing material very fast before you even take it into the different instruments. We've done actually quite a lot of tests. These tests were done at NASA Glenn. They have just superb vacuum testing facilities for dirty chambers. This one is specifically designed for drilling. We used one of our drills. The temperatures were around minus 100 centigrade. Hard vacuum. You also had the cold shroud, so as close to the lunar conditions as we can get. Idea was to drill down, capture icy soil, and send it to the couple of cups and to seal these cups and then measure how much we're losing during the transfer. This is the curve, the resultant curve. On the y-axis, you have, on one side, you have percent of water loss. On another side is theoretical sublimation rate and the ambient temperature on the x-axis. So we've been losing quite a bit. We've been losing 10, 20, 30%, depending on the temperature. So before, and the transfer time was essentially a couple of minutes. So from the moment you capture the sample to the moment you actually deliver to the cup, you're actually going to alter the water content inside the sample. So you really have to either do a very fast transfer or you have to keep everything at the very cold cryogenic temperatures. Otherwise, the material you're going to be analyzing will have a lot of volatiles lost. It's not just water. CO, CO2 sublimes at a much lower temperature. So you're probably going to lose even more. So a solution to all of this is so-called PVEx, or Planetary Volatile Extractor. It's essentially a coring drill. It's coring drill like you've seen in Home Depot and so on. And there is a reason for that. First one, it's mounted on a hammering drill, and that means it can cut through extremely hard materials. It's a coring system, which means the core is enclosed by the rigid walls, and also you do not cut entire surface material. You actually, the core material is, you don't really touch it. You don't have to spend energy grinding it down. You're only cutting a small sliver around the core. And finally, we have a swivel and slip ring to send the power and also to send volatiles out. And this coring system has a bunch of heaters on the inside. So as you drill down, you heat up the core, you volatilize all the material inside the core, you pressurize the system, and then because of delta P, volatiles go through the swivel into the cold finger. We've done a lot of drilling tests in analog simulants to the strength of different water content material on the moon. So we cut through ice, different limestones, and also annual HT2M. Our power is less than around 200 watt electrical, so mechanical is much lower than this. Penetration rate was extremely fast, a couple of centimeters per minute. So we can actually drill very, very fast down to a half meter or meter depth. And this is a test done in annual HT2M. On the right-hand side, you can actually see the drilling test. It's kind of sped up a little bit. But it's not like, when you see the drill going, it's not like you see the, paint drying on the wall. It actually goes really fast. You're not going to lose the concentration. And this is some of the data that we can get from a drilling. Essentially, by looking at the energy of drilling, I can tell you whether it's ice cemented ground or whether it's soil mixed with ice particles. And if it's ice cemented ground, we can actually tell you what's the concentration of ice. So this would be additional data point on top of the mass spectrometers and other instruments. In this particular system, PVEx is used to send volatiles to the mass spectrometer. We used Mylar balloon to show you that volatiles actually can flow into the mass pack. So instead of Mylar balloon, you can put a mass pack, and you have pretty robust system. This mesh pack with the PVEx can be mounted on a resource prospector, on a Viper rover, or on the landers. Here we have lander from Orbit Beyond and Astrobotic mounted alongside the leg, so it's just right by the surface. We can just drill down. We don't have to really deploy anything. We can drill down and send volatiles directly to the mesh pack. And in this particular case, this is volatile collection in a cold finger for in situ resource utilization, for actually mining. You can see these sort of white spots in radial spots. This is where water actually is being concentrated in a cold finger real time. We've done a bunch of end-to-end tests in a vacuum chamber as well. Extracted water. I wouldn't drink it. Actually, I didn't drink it. We sent it for analysis and still waiting for results. But the bottom line is, with this system, we can extract at least 50% of the water contained in the original material. And this is PVEx miner. Bunch of these PVEx mounted in front, so we can actually replace them if they break. And that's something like this that could follow on after Viper has done a reconnaissance on a moon. So in conclusions, PVEx can be used for prospecting, for delivering of volatiles to a mesh pack, and also for ISRU. And to my knowledge, this is the only system I've seen that has shown end-to-end capabilities for actually getting into the icy formation and also extracting of volatiles into the cold finger or mass spectrometer. So thank you. SBIR program. Picture on the right-hand side of the drill is upside down because we're going to the South Pole. And also the Mylar balloon, you had to turn it upside down to make it smiley face. Thank you.
All right, very good, Kris. Yeah.
Thanks.
Questions?
It was pretty obvious, my presentation. So.
Where were you doing the drilling at Glen too? Were you doing yours?
So this one is actually done in our facilities at Honeybee. We have a 3.5 meter vacuum chamber where we do all the tests before we send it to Glen. Obviously, we want to make sure everything works before we send something to NASA.
Yeah. Okay.
So that's one way we do that.
Do you guys ever measure enhanced electrical charging and interacting with the regolith with like a triboelectric effect or anything like that?
Actually, we have not, but I've seen, I was at the ISRU workshop last week, and I've seen that triboelectric charging could be a problem. So we're going to be working with the folks from NASA Goddard Space Flight Center to see actually if that could be a problem or not.
Okay, yeah, cool, good,
Yeah.
good, yep, neat. Anyone else? Brian?
Since I'm from down under, was that drilling in a vacuum?
Correct. So all the tests that you see with water extraction and delivery of volatiles, this is all done in vacuum. And actually, that's very, very important. We try to get to realistic conditions, and we always run tests in vacuum. And with frozen material, different water content, and we also make sure that material is prepared per NASA standards. So NASA Glen, Julie Kleinhans developed a process for preparing regolith with different ice concentrations, and we follow exactly the same process.
Very good. Parvati, you got a question?
Yeah, so do any of the volatiles stick to the instrument itself? I'm just imagining, if you're trying to get an idea of the distribution over some area between successive measurements, do you get any cross-contamination of sites?
No, you can actually get rid of volatiles by heating all your walls, and it happens very, very fast. It's actually amazingly how difficult it is to capture volatiles. A lot of ISRU systems I've seen, water extraction system, they focus on heating. Heating is not a problem. It's actually capturing volatiles is a problem. They go absolutely everywhere. Creating a hermetic system on the moon is extremely, extremely difficult. That's why a lot of, that's why we're seeing some losses.
So the 50% of volatiles that you don't capture likely move outward.
Yeah, so it's again, plumbing is leaky. It's very difficult to have all the swivels and fittings to be hermetically sealed. We probably have some losses also slightly at the bottom, but so you'll always have to assume you're gonna have losses. It's almost impossible to have it hermetically sealed and capture everything.
Cool, thanks.
Good question.
Great, very good. Any other
Umberto?
questions?
No, good.
Okay.
All right, thank you.
Yep, you bet.
Thanks.